gravitational potential energy. If I take the first case, close to the surface, we'll take the case close to the surface of Earth. Now, let's take a look how to calculate the gravitational potential energy. You have already seen this, how to work out the gravitational potential energy. Now, you know that close to the surface of Earth, gravitational field is uniform. So let's assume that this is the surface of Earth. So it looks flat because it's a small region on the surface of the Earth. So I can write surface. This is the surface of Earth. Now, let's assume that here the gravitational field is uniform. So what is this here? In this region, gravitational field is uniform. So I can write gravitational field is uniform. What does it mean by uniform? You have a specific value and written as G. Now we know that we need to work out the gravitational field strength close to the surface. Now we can see that the G value we can actually calculate using the standard equation. G is equals to, what is it? G m over r square. And if you substitute here, G is the universal gravitational constant, m is mass of Earth, mass of Earth, and r is approximately the radius of Earth. Radius of Earth. This is confusing. Why is it radius of Earth? This is approximately radius of Earth because this region, the height from the surface of the Earth is, assume that, let's take this point for example, we are lifting a body from the ground and you are lifting this body up to a height h, right? So this is the height. So this is the body now. Now the body is here. So I can draw this diagram. Here we have the body now. Now this is the height through which the body is moved. Now look at here compared to the radius of the Earth, because h is much smaller than the radius of Earth. Therefore, you can say r is approximately h. So you can say r is approximately the radius of Earth. Because actually, what is the value of r? We want to know the value of r. R is equals to radius of Earth plus h. So you don't really bother about the h when we calculate the g value. When you calculate the g value here, g is equals to gravitational constant times mass of Earth divided by square of the radius of the Earth, and this works out merely 9.81. Of course, meter per second square. This is actually the acceleration due to gravity. So you can see that g is equals to gravitational field strength, that is exactly the same as acceleration acceleration due to gravity. So that's how we get it as 9.81. Now let us look at the case where we lift a body through a height h. So these calculations, let us put in some boxes so you will not get. So here we have calculated the acceleration due to gravity. All right. And I have a bit of a problem here, which I will just sort this out because now I see it's messed up a little bit. I wish it a little bit more organized. So I'm not really bothered about it now. I hope it looks reasonably okay. We can write this as uh, meter per second square. Look at here. So we have calculated the acceleration due to gravity, and we have got the relationship. G is the gravitational field strength, that is exactly equal to acceleration due to gravity in here. So the all these pieces of information is very handy. All right, now let us try to work out the potential energy. So we are lifting a body of mass m and through a height h. So the force acting downward is the gravitational force, or here what is happening downward is the G gravitational field strength is acting, or the weight is acting downward, which is exactly equal to mass times the gravitational field strength. So the weight acting downward, W, everywhere within this region, W is equal to mass of the body times G. And you are lifting it up to a height. So it's very simple case now. So the work done against, look at here. So the first assumption we make, we assume that the gravitational potential energy is a very important assumption. Potential energy of a body on the surface on the surface of Earth is equal to zero. This is a very important assumption we make. Whenever we calculate potentials and potential energies, you should realize one thing: neither of them are absolute. We need to have a reference point where the potential is zero and potential energy is zero. These reference points are chosen with suitable to the frame of reference you work with. So in this case, if you're talking about motion of a body or close to the surface of a body, gravitational potential energy is on the surface of the earth is taken as zero. So if you want, you can write it here at the surface of earth. Where is the surface of earth? Here you can write gravitational potential energy of all bodies taken as zero. Now, the work done in moving this mass through this height will be stored in the body as gravitational potential energy now. Okay? So, second point you can write gravitational potential energy of a body of mass m close to the surface, that's only for close to the surface, close to the surface of Earth. It's true for any other planet or moon or anything, is close to the surface of Earth is obtained by the work done to move that body that body from the surface of Earth to a point, of course, against the gravitational force. The gravitational force is exactly equal to the weight. So, if you want to find out the gravitational potential energy of the body here, GPE, you need to find out how much work is done in moving this mass m against the weight, which is the force acting, and again the gravitational force, how much work is to be done in moving it through the height h and placing it at this point. So you understand that? So the force is actually W, that's exactly equal to the weight of the body, and the displacement is h. So we can just write in this case, so you can write gravitational potential energy is equal to work done, that is equal to force times displacement, that's equals to mg, that is the force, times displacement is h, this is equals to mgh. So we can write gravitational potential energy at a height from the surface of Earth is equal to G P is equal to mgh. Now this equation is valid only close to the surface of Earth. Why is it valid only close to the surface of Earth? Because we have assumed that the gravitational field strength close to the surface of Earth is constant. That's what we have. That's exactly equal to the acceleration of gravity. So just note that down. This works. This equation is valid. Put in a different color so you will not be confused. This equation or relationship is valid only close so close to the surface of Earth. Surface of I can write any celestial body. Any celestial body. Why? If you can think of the reason, that means you understand this idea. What is the reason? The reason is that I'll just mark it down here. The reason is that what is it? Gravitational field strength. This is uniform, uniform, close to the surface of Earth, close to the surface of Earth. These are the assumptions we have made, which are nearly true. Second thing, we have assumed that gravitational potential energy of all objects on the surface is zero. On the surface of Earth, surface of Earth is assumed to be zero. This assumption is equal to zero. So this is an assumption we have made. So only under these conditions that equation is valid. So this is the idea of gravitational potential energy close to the surface of Earth.